Okay. So for our code, we decided to add an extra bit to our ALU. So originally we just had the logical and arithmetic operations from the previous lab. We added the logical right and a logical left shift, and we went bits 1 through 4 for left and right for both A and B, and that was how we edited our ALU. Next, Koen's going to talk about our counter and trying to incorporate that to a
All right, so for our project, we implemented a counter, and basically we used the clock, and we basically on every output we can just implement. It just counts on the LCD screen, and so you can see the code over here implements it, and then yeah, and if we go to the top, this is for our. We tried to do the temperature sensor, but we found that we had issues with it because it was using a different clock. So if we had more time, we could have definitely found a way to utilize our original clock that worked with the counter, and then we would have also displayed it on the unused bits of the 7-segment display. All right.
The final thing was our state machine, where the state machine for our counter uses a 2-bit state just to check which of the 4 7-segment displays we're using. And the temperature sensor has this full state machine, which also uses a 2-bit state. And our main issue is trying to combine the two just because this one has a couple more conditions and always blocks that it's using, and we just had a hard time to combine those. I think if we had more time, we would be able to easily combine them, but we just didn't. Moving on to the actual code, or
The demo.
The demo.
Right. So here is the working clock counter, and you can see it's in hex, so it goes from 1 to F, and you can see it goes A, yeah, B, C, everything. And now Luz will show the new added features from our ALU.
So for ALU, we added on the 5th bit. So this is CN, and we have this would be mode. If you hit that, I believe we are on arithmetic left for 1 bit for A, if I'm not mistaken. Give me a second. Yeah, sorry, we're doing arithmetic right for A by 1 bit. So for example, if we hit 2, this first LED is C out, and then this next LED would be like 0001, which makes sense because if you have 2, which is 0010, and you shift it to the right by 1 bit, you get 0001. The same thing happens if we move it to 4.
It's because this has a reason.
I just said something wrong. Sorry. And then the same thing happens if we hit 4. So that's 4. As you can see here, it's 0010, which makes sense because then 4 would be 0100, so I move over 1 bit. And then for right shift, you can see there, that is right shift by, left shift, logical left shift by 1. Again, because now it's 1000, which would be 8, and that makes sense because if you shift 4 1 to the left, you get 8. And so that was just like a quick demonstration of how that works.
All right, and then we're gonna move on to the code of the temperature sensor, which we did in fact were able to push it onto the FPGA, but it just did not work with our code. So this is just how it should have been. And then for our project, if we go back to the rubric, oh yeah, sorry. You can see how the temperature does go up when he puts his finger in it. And, yeah.
Going back to discussion.
Okay, so overall, our project, for our input and output, we chose to change the output mechanisms. So we had the live display of the clock, the counter, which hasn't been done in the previous labs before. And for our design, we chose to modify the ALU, which Lewis showed the arithmetic shifts. And we also added sequential logic elements such as the counter, which used the finite state machine and the clock. And for our surprise, we tried to do the temperature sensor, but we didn't really quite get it in time. But yeah, is there anything you want to add?
that's about it. Yeah, I think if we had more time, I think we definitely could have included a temperature sensor. But I think overall, all the other three aspects we were able to pretty successfully do.
All right, thank you.
All right, thank you.